Hi friends, in this lecture we are going to study Z transform, in which we are going to see introduction, definition and some problems based on Z transform. So Z transform is a function which transforms a sequence to a function of a complex variable Z. It means that it's a function such that the input is a sequence and the output is a function of a complex variable Z. So Z transform is a discrete version of Laplace transform. So the Laplace transform is defined on the continuous functions where Z transform is defined on discrete function that is nothing but a sequence. So Z transform is used in the analysis of discrete time signals, voice transmission, solving difference equation, etc. So the flow of this lecture is, first we are going to define what is a sequence as Z transform is defined on a sequence. Second, we are going to define some operations on sequence. Next, we are going to talk about convergence and divergence of sequence. Then we are going to define what is called as a series. Then we are going to define Z transform. Then region of convergence of Z transform. Then some problems based on Z transform. So now let's see what is a sequence. So sequence is an ordered set of real or complex numbers. So it's a collection of numbers with some order. We will denote a sequence by a sequence f of k, or we can write this sequence as, if we take k is an integer, so if k is equals to 0 we get f of 0 comma then f of 1 comma f of 2 comma f of 3, and then on the left hand side of f of 0 is going to be f of minus 1, f of minus 2, f of minus 3 and so on. Okay, so these numbers are placed in the order. We have an element f of 0. So once we know what is the number at 0th position, we know the position of every other number. For example, if we take the sequence 5, 9, 13, 17, 21 and so on, or so here you can see that 5 is highlighted by red, so that element is nothing but f of 0. In while writing, you can just circle the element to show what is an f of 0, or you can put an arrow on the number which is your f of 0, because once you know f of 0, then you can identify what is f of 1, what is f of 2 and so on. So here you can write this sequence as f of 0 is 5, f of 1 is 9, f of 2 is 13, f of 3 is 17, f of 4 is 21 and so on. Another example is 0, 10, 15, 20, 25. So here f of 0 is 10. So f of 1 will be 15, f of 2 is 20, f of 3 is 25, f of minus 1 is 5, f of minus 2 is 0. Okay, see here we have a f of 1, f of 2, f of 3, f of 4, f of 5 are not defined. So by default we take that elements as a 0. Okay, so example 3, here we have 1, 2, 4, 8, 16, and so on. And here on the left hand side of 1, it's a 1 by 2, 1 by 4 and so on. So that is, we can write this sequence in the terms of formula or in a compact form like 2 raised to k, where k belongs to z. So if we take k equals to 0, 2 raised to 0 will be 1, 2 raised to 1 will be 2, 2 square will be 4 and so on. Note that example 1 is a one-sided infinite sequence. Example 2, so let's see the example 1. So this is an example 1 which is an one-sided infinite sequence. There are infinite terms only on one side of 0, f of 0. Okay, the second example, it's a finite sequence. It just contains finite number of terms. Then in example 3, it is a two-sided infinite sequence. As you can see on the right hand side, there are right hand side of f of 0 there are infinite element. Even in the left, on the left hand side of f of 0 there are infinite elements. So now we have defined a new object in mathematics which is nothing but a sequence. So once we define new objects, we talk about the operations on that objects. So our new object is nothing but a sequence. So now let's define how to add two sequences, addition and subtraction of sequences. So sequence f of k plus minus sequence g of k is equals to sequence of f of k plus minus g of k. So for example, we have a sequence f of k which is f of 0 is 0, f of 1 is 1, f of 2 is 3, f of 3 is 5 and so on, and f of minus 1 is 1, f of minus 2 is 1 and so on. And we have a sequence g of k where f of 0 is 1, f of 1 is 3, f of 2 is 5, and f of minus 1 is 2, and so on. Okay, so then the sequence f of k plus g of k will be, we have to add the 0th position element with the 0th position element, we have to add the 0th position element of f of k to the 0th position element of g of k. So it's going to be 0 plus 1 will be 1, and then the first f of 1 will be added to g of 1. So 1 plus 3 will be 4, 5 plus, so yeah, 3 plus 5 is going to be 8. So this is how the corresponding elements get added. Okay, and this is nothing but how it defines the addition of a sequence. Scalar multiplication. So if A is a scalar, then a scalar into a sequence is equals to, it's a sequence of A into f of k. It basically says that A will get multiplied to every number in this sequence. So for example, if we have A equals to 2 and sequence 0, 1, 3, 5, and on the left hand side we have 1, comma 1, comma 1, and so on. So then A into f of k, which is equals to A into sequence f of k, which is equals to sequence of A f of k, and we just have to multiply 2 to the every element of this sequence. So we get 0, 2, 6, 10, and so on. So now this is an important part, a convergence and divergence of the sequence. So a sequence f of 0, comma f of 1, comma f of 2, comma f of 3, and so on is said to be convergent if there exists a belongs to real number. So we are basically talking about a sequence in real number. F of 0, f of 1, f of 2, f of 3 are real numbers. So it's said to be convergent if there exists a belongs to real numbers such that f of k tends to a as k tends to infinity. So as k tends to infinity, f of k value is moving towards a. Or in the terms of limit, we can write it as limit of k tends to infinity, f of k exists. So if this limit exists, we say that the sequence is convergent and it converges to a, and that a value will be nothing but the limit value, limit of k tends to infinity, f of k. Or otherwise, if there is no such conditions, so then we call it as a sequence is divergent. So example 1, we have a sequence f of k is equals to 1 comma 1 by 2 comma 1 by 3 comma 1 by 4, and so on. So now if we calculate limit of k tends to infinity f of k, so we can see that the value is 0. Okay, the limit of k tends to infinity, because as the denominator gets increases, 1 upon the denominator will get converges to 0. Okay, so sequence f of k is convergent and it converges to 0. Example 2, we have a sequence f of k equals to 1 comma 4 comma 9 comma 16, and so on. So here we can see that f of 0 is 1. So limit of k tends to infinity, f of k is infinity, as the value of the sequence is getting increase, and the limit tends to infinity because the sequence is nothing but k square. So as k tends to infinity, k square goes to infinity. So this sequence f of k is divergent. Example 3, we have a sequence equals to 0 comma 1 comma 1 by 2 comma 1 by 3 comma 1 by 4, and so on. And on the left hand side of 0 it's a 1 comma 1 comma 1, and so on. So this is a two-sided sequence. So such a sequence is said to be convergent if limit of k tends to infinity f of k and also limit of k tends to minus infinity f of k both exist. So in this case we can see that limit of k tends to infinity f of k is 0, because as k tends to infinity 1 by k tends to 0, and limit of k tends to minus infinity f of k is 1, because on the left hand side of 0, which is f of minus 1 is 1, f of minus 2 is 1, and so on, all the values are 1, so the limit is 1. So this implies that the sequence f of k is convergent. Remember, if any one of them is divergent, so then the sequence will be divergent. So now let's define what is a series. So series is an infinite sum represented by an expression a1 plus a2 plus a3 plus, and so on. So it's an infinite sum which can be written in the compact form summation of k equals to 1 up to infinity ak. So a series is said to be convergent. A series is convergent, basically it means to say this infinite sum is finite if the sequence of their partial sum sk is convergent. So sequence of partial sum is s1, which is a1, s2 will be a1 plus a2, s3 will be a1 plus a2 plus a3, and so on. So if the sequence of partial sum is convergent, we say that the series is convergent, because as you can see, if we take limit of k tends to infinity sk, so that is nothing but a1 plus a2 plus a3 plus up to ak, and we are taking k tends to infinity, so basically we are adding all the terms. So the limit of k tends to infinity sk, if it exists, so that value is going to be a1 plus a2 plus a3 plus and so on. So that infinite sum will be finite if that limit exists, and otherwise it is called as a divergent. Definition of a Z transform. So Z transform of a sequence. So Z transform is defined on a sequence. So we are taking sequence f of k, and Z is a complex number which is of the form x plus iy. So then Z transform of sequence f of k is equals to summation of k equals to minus infinity to infinity f of k upon z raised to k. So here we can see that input is a sequence and the output is a function of z. So this series is a special series which is called as a Lorentz series at point z equals to 0. This is a special series. We will talk about that little later. So now we can write this summation as, if we take k equals to 0, so we get f of 0. If we take k equals to 1, we get f of 1 upon z, plus when we take k equals to 2, it's an f of 2 upon z square plus f of 3 upon z cube and so on. And if we take minus 1, so we get f of minus 1 into z, because z ratio 1 upon z ratio minus 1 will be z. And then if we put k equals to minus 2, we get f of minus 2 into z square and so on. So here f of z, okay, basically we are denoting this series as a capital F of z. So the z transform of sequence f of k is capital F of z. So here f of z is a Lorentz series expansion of some complex number z at z equals to 0. So now what we want, when we find a z transform of a sequence, we get this as a function which is the function of z. Now we are interested in all those z values for which this infinite sum is finite. It is same as when we have some function like 1 upon z minus 1. So we talk about its domain, basically all the values of z for which it gives the nice answer. So we just take all the complex number except 1, because at the 1 upon z minus 1 is not defined. So we are interested in finding all those z values for which this infinite sum is finite. So f of z is a function of the complex variable z and is defined only if the sum is finite. That is, the infinite series is absolutely convergent. So absolutely convergent means summation of k equals to minus infinity to infinity mod of f of k upon z raised to k converges. Okay, the mod of a complex number, basically if z is equals to x plus iy, so the mod of z is square root of x square plus y square. So the region for which summation of k equals to minus infinity infinity f of k upon z raised to k is convergent is called the region of convergence, denoted by ROC. Okay, here we are calling it as a region because we are working in a two-dimensional space which is a complex plane. So we are going to talk about those region for which this infinite sum is finite. So as we have a Lorentz series at z equals to 0, so the special thing about this is it converges on the open annulus region z such that r is less than mod z is less than capital R. So annulus region is a set of all those complex number which lies between small r and capital R, whose modulus lies between small r and capital R. So it looks like this. So imagine that this is our complex plane. So mod of z is here we have an origin here 0, and mod of z is greater than r, small r. So it's outside this, and it is less than capital R. So it's an inside this. So this highlighted region or the shaded region is the region of convergence. So if you have a Lorentz series expansion, so its region of convergence is always going to be of this form. It is going to be of annulus form, which is nothing but a region between two concentric circles. So if you take any point outside this capital R value, so this infinite sum will be infinite. And if you take any value inside this circle, inside this small circle R, so again this infinite sum will be infinite. So only on this shaded region, this infinite sum is finite. So here we have small r less than mod z less than capital R. So it says that even that small r can be 0 and the capital R can be infinity. So if we suppose this capital R is infinity, so how this analysis region is going to look like? See here, imagine that this dotted is a circle of radius small r and there is no upper boundary, it's an infinity. So the highlighted region is the region of convergence. The small r can take a value 0 and here we are taking a small r again. Okay, so the mod z is greater than 0, it's less than small r. So now this highlighted region is going to be the region of convergence. Here we cannot include 0 because here there is no equality. Next, if we take small radius as a 0 and capital R as an infinity, so then the region of convergence is nothing but the complete complex plane except origin. Okay, so these are the possible region of convergence for classified in the terms of values of small r and capital R. So now let's define what is an inverse Z transform. So if Z transform of f of k, sequence f of k is given by summation of k equals to minus infinity to up to infinity f of k upon z raised to k, which is our function f of z. So then inverse Z transform of f of z is equals to sequence f of k. So now you are running in the opposite direction. In the Z transform, the input was a sequence and the output was a function of z. In the inverse Z transform, input will be a function of z and the output will be a sequence. So now let's solve some problem based on Z transform. Let's solve this problem if sequence f of k is equals to 9, 6, 3, 0, minus 3, minus 6, minus 9. So here we have f of 0 is 3. Find Z transform of sequence f of k. Okay, so here we can just write this sequence as what is f of 0? So f of 0 is 3, f of 1 is 0, f of 2 it's a minus 3, f of 3 it's a minus 6, f of 4 is minus 9. We don't talk about f of 5, f of 6 since the sequence is not defined for 5, 6, 7, 8 and so on. So we have f of minus 1 which is equals to 6, f of minus 2 is equals to 9. So Z transform of sequence f of k is equals to summation of k equals to minus infinity to plus infinity f of k upon z raised to k, which can be written as f of 0 plus f of 1 by z plus f of 2 by z square plus f of 3 by z cube plus and so on. And on the left hand side of f of 0 is f of minus 1 into z plus f of minus 2 into z square plus and so on. So now we just have to substitute the values. So f of 0 it's a 3 plus f of 1 it's a 0, so 0 by z will be 0. F of 2 it's minus 3, so it's a minus 3 upon z square plus f of 3 is minus 6 upon z cube plus f of 4 is minus 9 upon z raised to 4. Then on this side we have f of minus 1 which is 6 into z plus f of minus 2 which is 9 z square. So now this is nothing but 9z square plus 6z plus 3 minus 3 by z square minus 6 by z cube minus z cube minus 9 by z raised to 4. So this is the z transform of the sequence f of k. Now after finding z transform we have to show what is the region of convergence. So we are talking about all those points for which the z transform function is well defined. So now in this case this sum is finite, so there is no infinite sum here. So we just have to talk about all those z for which every term is well defined. So if we see that 9z square plus 6z plus 3, this is well defined for any complex number, but if we see the last three terms, they are not defined if z equals to 0. So then what is the region of convergence? So the region of convergence will be the complete complex plane except 0. Okay, so in the analysis form it can be written as 0 less than mod z less than infinity. So it contains all z all it contains all complex numbers except 0. So here the small r value is a 0 and the capital R value is a infinity. So in the last problem, it was a easy problem just because the sequence was finite. So we easily got the region of convergence. Now when we have a infinite sequence, so first we are going to find the Z transform. Then by using expansion of some standard functions that we have studied, the Maclaurin series expansion, we are going to use that to get the region of convergence easily. Okay, so now let's recall some of the standard series expansion. So we have first one a plus ar square plus ar cube plus and so on, which is the sum of geometric progression. So this value, so this infinite sum is finite if mod r is less than 1, and that finite value is a upon 1 minus r. So we can write, so the value of a plus ar square and so on, the value of this is a upon 1 minus r if mod of r is less than 1. Similarly, if 1 plus z square plus z cube plus and so on, which is a particular case of first, so we get the value of a is 1 and the value of r is z. So the value will be 1 upon 1 minus z if mod z is less than 1. Third one, it's just replacing z by minus z. So again, if mod z is less than 1, so the 1 minus z plus z square minus z cube plus and so on. So the value of this will be 1 upon 1 plus z. Then 1 plus z raised to n. So this is equals to 1 plus nz plus n into n minus 1 upon 2 factorial z square plus n into n minus 1 n minus 2 upon 3 factorial into z cube plus and so on. So if n is a natural number, so then this infinite sum is anyway finite, which comes from the binomial theorem. So here we are talking about those n which are less than 1 or some irrational number or some rational number other than natural number. So this infinite sum is finite if mod of z is less than 1. Next, e raised to z is equals to 1 plus z square by 2 factorial plus z cube by 3 factorial plus z raised to 4 by 4 factorial and so on. So this infinite series converges, or this infinite sum converges for any complex number z, and that value is nothing but e raised to z. So there are few more. So log of 1 plus z. So log of 1 plus z is z plus z minus z square by 2 plus z cube by 3 minus z raised to 4 by 4 plus z raised to 5 by 5 minus and so on. So even this infinite sum is convergent for mod z less than 1, and that convergent value is log of 1 plus z. And just replacing z by minus z, we get 7. So 8 is a particular case of fourth. We can see that if we take n equals to minus 2, we get 1 plus 2z plus 3z square plus 4z cube plus 5z raised to 4 plus and so on, as the terms occurs in a nice pattern. So we will use this we will use all these expansions of some standard functions to get the region radius of convergence or the region of convergence of the Z transform. So now let's start with this problem. If sequence f of k is equals to 4 raised to k for k less than 0, 3 raised to k for k greater than equals to 0, find Z transform of sequence f of k. Okay, so sequence f of k is given. So now let's write down in the form what is f of 0. So f of 0 is going to be k comes under k greater than equals to 0. So it's a 3 raised to 0. It's going to be 1, comma. So then k equals to 1 again. So here we have 3. Then k equals to 2. So it becomes 3 square. Then it's a 3 cube. Then it's a 3 raised to 4 and so on. And then for negative integers, for k equals to minus 1 is going to be 4 raised to minus 1. So it's going to be 1 by 4, comma. Then minus 2. So it's going to be 1 upon 4 square, comma. Then 1 upon 4 cube, comma, and so on. Okay. So here this is our 0th position element. So now we have to find the Z transform of sequence f of k. So Z transform of sequence f of k is equals to summation of k equals to minus infinity to infinity f of k upon z raised to k. Okay, so this is nothing but let's write this summation form as a f of 0. What is k equals to 0? We get f of 0 plus k equals to 1. We get f of 1 upon z. For k equals to 2, we get f of 2 upon z square, plus for 3 we get f of 3 upon z cube, plus and so on. Then on this side we have f of minus 1 into z, plus f of minus 2 into z square, plus and so on. Okay, so now let's substitute these values here. So we have f of 0 is 1, so it's a 1, plus what is f of 1? It's a 3, so it's a 3 by z, plus then it's a 3 square by z square, plus f of 3 is a 3 cube by z cube, plus and so on. Now here f of minus 1, it's a 1 by 4, so we get z by 4, plus then here it's a z square by 4 square, then plus z cube by 4 cube. Okay, so this is the z transform of the given sequence. So now what we have to find? We have to find region of convergence. We have to find those values of z for which this infinite sum is a finite. So now what you have to do after finding z transform, you just have to identify the structure of the series with the standard series. I think we saw around 7 to 8 standard series, so you just have to identify that it is in which form. Okay, so here we can see that it's a 1 plus I can say it's a z, then it becomes a z square, then plus z cube. So it is of the form the series 1 plus z square plus and so on. So the answer for this was 1 upon 1 minus z for mod z less than 1. Okay, so now as we can see that here there is a infinite sum on the right hand side and there is a infinite sum on the left hand side. So we are going to break this infinite sum into two infinite sum. So it's easy to identify this, that we are going to just start from 1 and let's take this part first and then the remaining part as a second. Okay, both are in the standard form. So now what we have? So we have, let's write this as a 1 plus 3 by z plus 3 by z the whole square plus 3 by z cube, plus and so on, then plus what, let's write this addition in the reverse order. So we are going to get z by 4 plus z by 4 the whole square, plus z by 4 the whole cube, plus and so on. Done. So now we can see that the first one is of the form 1 plus z square plus z cube. So this infinite sum is finite for mod z less than 1, and that finite sum is 1 upon 1 minus 1 minus z. And what we have in place of z here? We have a 3 by z. So here we are going to have 3 by z, plus. Now in this case, it's of the form a plus ar square and so on. So the value of a is z by 4, the first standard expansion, upon a upon 1 minus r. Here a and r are same. Okay, so we get this value. So now what we want to know is that this infinite sum, this one, this part, this infinite sum, it turned out to be a finite part, but this happens when mod of 3 by z has to be less than 1. Okay, next it's a z by 4 plus this part, this infinite sum is finite when mod of z by 4 is less than 1. So we want both condition to get satisfied, then only this sum will be finite plus this sum will be finite and the overall addition will be finite. So now what we get? So if we see this condition, so we are going to get 3 less than mod z because mod of 3 is 3 and mod z is less than 4. So we have we want mod z to be greater than 3 and mod z to be less than 4. So that is nothing but 3 less than mod z is less than 4. Okay, so here we get our value of small r and the value of capital R. So now if we go to the complex plane, so now what we have a circle of radius 3 we have a circle of radius 3 and then a circle of radius 4. So where our z lies? Z lies between radius 3 and radius 4. Sorry. Okay. So this is the region of convergence. Means if you take any point from this region, this infinite sum will be finite. If you take any point outside this region, so this infinite sum will be infinite. Even if you take even if you take 0 here, you know that here it's a 3 by z square, so this all thing will become infinite and the addition will be infinite. Okay, so now we can just simplify this. We just by simple calculation we get z upon z minus 3 plus z upon 4 minus z, where the region of convergence is 3 less than mod z is less than 4. Okay, so this is our complex. So you can note down this problem, a similar problem for the exercise. Find the z transform and the region of convergence of the sequence f of k, where 5 raised to k for k less than 0 and 3 raised to k for greater than equals to 0. So now let's find z transform of some standard functions. So the first one is a unit impulse function, which is defined as delta k equals to 1 for k equals to 0 and it is 0 otherwise. So now let's first write down the sequence. So we have delta of k as 1 for k equals to 0. So if k equals to 0, we are getting 1. Now for k equals to 1, so the answer will be 0. For k equals to 2, answer will be 0. Then for 3, again it's a 0. And for minus 1, it's a 0. For minus 2, it's a 0 and so on. So let's just mark the 0th position element. So delta of 0 is 1. So now we have to find the z transform of delta k. So the z transform of delta k of the sequence delta k is equals to, it's going to be summation of k equals to minus infinity to plus infinity delta of k upon z raised to k. Okay, so now this is equals to, as we know for all non-zero k, as we know for all non-zero k, the value is 0. So we are just going to have for delta of 0. So for delta of 0, the answer is 1 upon z raised to 0, it's again 1. So z transform of delta of k is 1. And then what will be the region of convergence? So the region of convergence, now this is well defined for any z since it's a constant function. So region of convergence is the complex plane. So now we can write this as the z transform of delta of k is 1. So then inverse z transform, so the inverse z transform of 1 will be delta k. So it says that inverse z transform of 1 is unit impulse function. So now next standard function is discrete unit step function, which is defined as h of k equals to 1 for k greater than equals to 0 and it is 0 for k less than 0. So what is going to be h of 0? H of 0, it comes under 0 is k, comes 0 comes under k greater than equals to 0, so it's a h of 0 will be 1, then h of 1 will be 1, then h of 2 will be 1, h of 3 will be 1 and so on. But h of minus 1 will be 0, h of minus 2 will be 0, h of minus 3 will be 0 and so on. So let me mark the 0th position element h of 0. So now what we have to find? We have to find z transform of sequence h of k. So z transform of sequence h of k is going to be summation of k equals to minus infinity to plus infinity h of k upon z raised to k. So now this is equals to, as we know for all the negative integers, h of k is 0. So let's write the non-negative one. So h of 0, we are going to get h of 0 plus h of 1 upon z plus h of 2 upon z square plus h of 3 upon z cube plus and so on. So we know that h of 0, h of 1, h of 3, h of 2, h of 3 and all are 1. So we get 1 plus 1 by z plus 1 by z square plus 1 by z cube plus and so on. So this is again of the one of the standard form. So which is nothing but 1 plus 1 by z. We can just write it in the nice form so that it's easy to identify the structure. it's a 1 by z cube plus and so on. So we know the expansion of the value of 1 plus z square plus z cube, which is 1 upon 1 minus z. So here we have 1 plus, we have 1 plus, it's a z. I am calling 1 by z as a z. Then 1 plus z square plus z cube and so on. So what we are going to get this as, it's going to be 1 upon 1 minus z. Okay, for mod of 1 by z is less than 1. Don't forget this condition, because from here only you are going to get the region of convergence. So now this is equals to z upon z minus 1, and here we are getting 1 less than mod z. So now it says that the region of convergence, as you just have a lower boundary, okay, it's bounded by 1, so this is our small r, and there is no upper boundary, that means that a capital R is infinity. Okay, this is nothing but less than infinity. So now we have a circle of radius 1, we have a circle of radius 1, and then mod z is greater than 1, so the region is outside this circle. Okay, this is a complex flow. So next problem is find the z transform of sequence f of k equals to k into alpha raised to k, where k is greater than equals to 0. So here sequence is defined only for k greater than equals to 0. We are not going to talk about -1, -2 and so on. So now let's first write our sequence explicitly. So we are going to get f of 0 as a 0. Okay, f of 0 is 0. This is our 0th position element. So then k 0, so we get 0, k equals to 1, so we are going to get alpha. For k equals to 2, we are going to get 2 alpha square. For k equals to 3, we are going to get 3 alpha cube. For k equals to 4, it's a 4 alpha raised to 4 and so on. Okay, so now what we have to find? We have to find z transform of the sequence f of k. So z transform of sequence f of k is equals to, given by summation of k equals to minus infinity to plus infinity f of k upon z raised to k. So now this is equals to what it is. It's going to be f of 0. We are not talking about negative integers, just because sequence f of k is defined for k greater than equals to 0. So we are going to have f of 0 plus f of 1 upon z plus f of 2 upon z square plus f of 3 upon z cube plus and so on. Okay, so now here we are going to get f of 0 as 0, then f of 1 is alpha by z, then f of 2 is it's a 2 alpha square by z square plus 3 alpha cube by z cube plus and so on. So this is the z transform of the given sequence. Now if we see that, if we compare this with the standard expansions, so it somewhere looks like 1 plus 2x plus 3x square plus and so on. This value was 1 upon 1 minus x square. Okay, so now from here, by just comparing, we can see that we just have to take alpha by z common. Okay, maybe I have written earlier, I have written this expansion in the terms of z. Here I have just written in the terms of x. Okay, so now here we take alpha by z common, so we are left with 1 plus 2 times alpha by z plus 3 times alpha by z square plus and so on. So now this is equals to alpha by z. Now we can see that this infinite sum is of this form. So as the value of x is alpha by z, so the answer of this is going to be 1 upon 1 minus x value, which is alpha by z square. Okay, so again, this infinite sum was finite for mod x less than 1. So what we are going to have here, we are going to have mod of alpha by z should be less than 1. So now here by some simplification, we get here denominator, we are going to get z minus alpha square, and that z square goes in the numerator, and then we are going to get as an alpha z. Okay, so this happens for mod alpha is less than mod z. So now in the complex plane, we want a circle. of radius mod alpha and z mod z is greater than mod alpha, and there is no upper bound, so it's nothing but capital R is infinity. So for all these values of z, this above infinite sum is finite, means it is well defined function. Okay, so this was all about the part 1 lecture of the z transform. In the next part we are going to take some more problems based on z transform. We are going to see properties of the z transform. Thank you.